Okay, in this section we're going to talk about linear combinations, and in particular linear combinations of vectors. Now, we have talked about what it means to add and multiply vectors. We're going to combine these two operations to form something called a linear combination. And this is fundamental to linear algebra. We'll be working with this throughout the course. Linear algebra, you could say, is in some sense the study of linear combinations. All right, so let's go to this definition of linear combination of column vectors. Right? So here we have a set of n column vectors, and we'll see some specific examples of this later. N column vectors from Cm. What does Cm mean? It means that there are m components, or m entries. And we also have n scalars. Notice there's one scalar for each vector. Okay, n scalars. Now, the linear combination associated with these vectors and these scalars is written this way. Take the first scalar, multiply by the first vector, second scalar, multiply by second vector, all the way up to the nth scalar, multiplied by the nth vector, add them together, and that's your linear combination. Now notice that a multiple of a vector is still a vector. So this is a vector, this is a vector, this is a vector. You're summing vectors. This is a vector. Okay, you're just adding them together. You're just combining them. Okay, so here's some examples of linear combinations. The constants are specified here. These are the factors that will multiply the vectors. We also specify Vor vectors here. To find a linear combination, as it says above, you take the first constant times the first vector, plus second constant times second vector, plus third constant times third vector, plus fourth constant times fourth vector, and that's expressed in this equation here. Now we know how to multiply constants by vectors. We're actually going to multiply this one by each entry individually, etc. We're going to multiply this minus 4 by each entry individually. We're going to multiply this 2 by each entry individually. We're going to multiply this minus 1 by each entry individually. And then we're going to sum the corresponding components of all the vectors. So we'll see how that works on down here. Here the vectors are multiplied. And then here the components are added. 2 minus 24 minus 10 minus 3 is minus 35. 4 minus 12 plus 4 minus 2 is minus 6. You can check all the answers, and we have a linear combination. Now you can form different linear combinations of the same set of vectors using different constants, and you'll get a different result. Right? So this is actually very important, that you keep the set of vectors fixed, and you use different sets of scalars. You get lots of different vectors. And we're actually going to study that set where you have a set of fixed vectors and you use all different possible sets of scalars. What does that set give you? So we'll talk about that later. Okay? So let's see how this is going to work out. So the question is, suppose I have these 4 vectors which are fixed, 1, 2, 3, 4, and I'm thinking of the linear combinations of these vectors. So I can ask the question, what vectors can I get as linear combinations of these vectors? In particular, can I get this vector as a linear combination of these 4? So that's a valid question. Okay. Now, of course, this W is just one particular vector. You could ask, can you choose any old vector from C6? We have to choose a vector in C6 because the vector has to have 6 components in this particular case. Could we choose any old vector in C6 and obtain that as a linear combination of the vectors that are given here, of the 4 vectors that are given here, 1, 2, 3, 4. Okay. So these are 2 very important questions, and they relate to what we've been talking about in a very intimate way. Right? point. So let's look at a particular example. Archetype B. Okay. Let's go back and take a look at what archetype B is. So I've moved back to archetype B. We have a system of equations, and we know we can associate this with a matrix. We have a matrix of coefficients, and we have a vector of constants here. So we can form an augmented matrix as well. So keep in mind this system of equations. Now here we've simply rewritten that system of equations. Sorry, let me go back here. Here we've simply rewritten that system of equations using the language of vectors. We had 1, 2, 3 equations, and we're writing that as the 3 components of a column vector, and the constants correspondingly were 3 components of a column vector. Now, this is a vector, but we can express it as a linear combination of vectors. First of all, we separate out all of the parts that have x1, and that's right here. Then we separate out all the parts that have x2. Actually, there's a 0 down here, and that's here. And then we separate out all the parts that have x3, and that's right here. And then we leave the column vector here the same. Now notice these entries here all have an x1 in common. So we could factor out the x1. These all have an x2 in common, could factor out the x2. Here we factor out the x3, and we get a result like this. Now this is super. What we've done is we've taken our system of linear equations and related that to the linear combination of column vectors. Okay? So we can actually interpret the problem of solving a system of equations as determining whether or not we can find a linear combination of these 3 vectors that gives us this vector. Okay, so we've transformed the problem. We have a different conceptual way of framing the problem. That the problem of finding a solution to a system of linear equations is the same as determining whether or not a certain set of vectors can produce another vector via linear combination. Okay. Now we did find a solution for archetype B, and these will be the coefficients of the linear combination that gives us the constant vector here. Okay, so if I put this -3 in for this x1 coefficient, this 5 in for this x2 coefficient, this 2 in for x3, I'm going to get a linear combination, and you can work this out, that this linear combination yields the vector on the right-hand side. Another important point here is that these are the only scalars because we've shown previously that there's a unique solution to the system. Any solution to the system will give us a set of scalars that gives us a linear combination that gives us the vector. Okay. Notice the 3 vectors are actually the columns of the coefficient matrix. Okay. So there's a very important relationship between the column vectors of a matrix and the matrix itself. So we'll be exploring that as we go along. Okay, here we go through the same discussion with archetype A. I'm not going to go back there, but this was the archetype A, and we're now writing it again as a quality of vectors, the 3 equations. Each equation corresponds to 1 component of the vector. We break up this left-hand side into 3 parts according to the variable, and we factor out the variable. So hopefully you can follow the steps of going from here to here and then to here. It's the same as in archetype B. Okay. And it turns out in archetype A that there are infinitely many solutions. So in fact, there are infinitely many choices of these coefficients that produce a linear combination that give us this vector. Okay. So here are some different possibilities for coefficients, and you can check this out that this actually works. Now notice something interesting here. If we use these 3 coefficients 2, 3, 1, and multiply by the given vectors, we get 1, 8, 5. If we use these three coefficients, 3, 2, 0, we also get 1, 8, 5. Okay, so we can set these all equal to each other. Now let's take the right-hand side and subtract it from the left-hand side. Okay. So these are the three terms in the left-hand side. These are the three terms in the right-hand side. Now, when I take the vector and subtract it from something that's equal to it, I'm going to get the 0 vector. This is the same, when I do this, it's the same as 185 minus 185, which is the 0 vector. All right, now this looks kind of complicated, but notice that we have this vector and another copy of the same vector, simply with a different coefficient. So 2 times 1, 2, 1, and we have minus 3 times 1, 2, 1, and that gives us minus 1 times 1, 2, 1. Same with this second pair. I have 3 times minus 1, 1, 1, and here I have minus 2 times minus 1, 1, 1. That gives me this result. Here I have a multiple of 2, 1, 0, another multiple of 2, 1, 0. I get this multiple of 2, 1, 0. So what do we have? We have a linear combination of our three starting vectors that gives us the 0 vector. Okay. So that's a very important point, that we have these three vectors that give us a linear combination that is the 0 vector. Now, we've been relating back and forth between vector equations and the original system of equations. Now, notice if you wrote this as a augmented matrix, we'd have the same coefficient matrix as we started with, and we'd have the 0 on the right-hand side. So what do we have here? Here we have a homogeneous system. We have a system where the constants are 0. And minus 1, 1, 1 is a solution. It's a non-trivial solution to the homogeneous system. Okay. So let's go down and see what's going on. All right, so it's good to keep these two examples in mind. And let's summarize the general behavior that these two examples illustrate. And that's the theorem here. So this is going to be the capstone of this video. And this basically restates in general form what we've already mentioned before. All right? So let's go through it. Now, denote the columns of a m by n matrix A as A1 up to AN. So you take your matrix here, you pull out the columns, and each column is going to be a vector. Okay. Then, x, n-dimensional vector x, is a solution to the linear system LS of AB. Remember what this means. This means a solution of the form AX equals B. So we can find a x such that AX equals B if and only if B is the linear combination of the columns of A formed with the entries of x. Okay, so we take this vector x, we use that as the coefficients, as the constants in our linear combination, and we combine the columns of the matrix according to these constants, and we get B. So if we're able to do that with these column vectors and with these coefficients, then that means that x is a solution to this equation, AX equals B. And then, all right, so that's really what we've been showing above. Here's the proof. Let me go through this quickly. So really what he says here is that this proof is just really a question of you're writing the same thing in two different notations. Okay, this is the system. This is the system of equations that you have originally, and you can write that in this form. Okay, we saw how you can take this. You can write this as a vector equality, where this vector is equal to this vector. Okay, then we can break apart this vector as a linear combination of different vectors. So we can write this system of equations in this form. and vice versa. If we have this form, we can rewrite it in this form. So really, this is just about equivalent notations. Okay. All right, and the fact that they're equivalent, we went through and showed how we're actually using the linearity properties, the properties of combinations of vectors, the vector operations to show that these are in fact